video set, we looked at density along a straight line, like a bar or a rod. Now we're going to talk about a different kind of density. We're going to talk about radial density, which we're assuming that we have an axially symmetric plate. So what do I mean by that? We're going to have a plate that is a perfect circle, and the density, how dense this place is, only depends on how far away you are from the origin. So if right here is the origin, all the points here in this pink marker, they all have the same density function, which I'll call sigma of r. So the density here is the same as the density here, is the same as density here, is the same as density here, is the same as the density here. Here's another circle. The densities here are all going to be the same. On the boundary, all the densities are going to be the same. So once again, the density only depends on how far away you are from the center, the distance r. And so what we want to do is that we want to calculate out the total mass of this plate, assuming that we know what the overall radius is, and we have this density function. We want to find the overall mass of this plate. And so the thing that we're going to do is that I'm going to do my best to draw two concentric circles that are very close together. So in the previous part, we were thinking about a little chunk of the axis is what we were dealing with. Now we're dealing with not a little chunk of the axis, but a little thin ring. Okay, so first question is, what's the area of this thin ring? So let's say that R1 and R2 are the radii, or the inner, oops, let me spell that right. Inner radius is R1, the outer radius is R2. So how we find the area of the thin ring is that we do the area that is inside R2, the outer part of the ring, minus the area that is inside of R1. And so, of course, we know what the formula for areas of circles are. And so this is just going to be pi times R2 squared minus the area of the inside circle is pi times R1 squared. And so this right here, this is the area that is inside this ring. So in between, let me shade it a little bit. That area going all the way around, this has area pi times, let me get that right there, pi times R2 squared minus R1 squared. And we have a difference of two squares, so high school algebra says that we can rewrite this as R2 minus R1 times R2 plus R1. Okay, so far we have the area here. And we're going to think of taking R1 and R2 to be really close together. So I'm just going to call R1 minus R2, I'm going to call that dr. We're thinking of that as something that is going to 0 here. Also, R1 plus R2, let me adjust the piece of paper, this is equal to 2 times, so I'm going to do something a little bit, that might look a little bit silly at first glance here, 2 times R2 plus R1 divided by 2, because this is, right here, is the average value of the average radius on, more or less, on our ring. Okay, so now let's think about how do we compute the mass. The mass is going to be density times area, and previously we found that our area was pi times 2 times, I'm going to call R2 plus R1, I'm going to call this R bar for the average value of R. So 2 times r bar. And then the density, we're going to approximate it. We're going to approximate it with the density at the midpoint of our two r values. And oh, I'm also forgetting, what did I forget here? On the area calculation, we need a dr. So at this point, we have to add up all of these masses. This is our approximation for the mass over any thin ring here. We have to add up all of these little masses, but adding up all of these little masses is just, we interpret that as an integral. And so the total mass as an integral is the integral from 0 to r, where r we're thinking as the overall radius of our plate. The integral from 0 to r of this up here, where we replace r bar with just a lowercase r. So 2 pi times sigma of r times r dr. And so this is the formula that we want here, or whenever we are dealing with radial densities, and we want to find the total mass. So why is there a factor of 2 pi r there? Basically, the outer rings are larger than the inner rings, so overall the outer rings contribute relatively more to the total mass. Okay, so that's all the setup. Let's go ahead and do a calculation with this. So a city's radial population density is given by rho of r. Here I'm using rho instead of using sigma as before. That shouldn't bother us. Times 500 times 1 plus r squared to the minus 1/2, where r, that is the distance from City Hall in miles. So how many people live between 2 and 3 miles from City Hall? So we're going to use the same setup here, except that instead of integrating between 0 and r, we're going to integrate from 2 to 3, because that is how far out that we need to go. But everything else, 2 pi times the density times r, everything else is going to go through in exactly the same way. So let me just do the work on this piece of paper. So how many people, so instead of doing, counting people, it's like counting the mass here. So the mass, the population, is the integral from 2 to 3 of 2 pi times r times the density, 500 times 1 plus r squared to the minus 1/2 dr. Okay, so all we have to do at this point is evaluate this integral, and this is a relatively straightforward one to do with u is 1 plus r squared. So then du is 2r dr. So 2 and r and dr, there is our du. And so what do we end up with? I can move the 500 pi out in front, times the integral of u to the minus 1/2, and all of that becomes du. Also, we need to change the bounds here. So when r is 2, u is 1 plus 2 squared is 5. And when r is 3, u is 1 plus 3 squared is 10. So here is our calculation we have to do to finish this off. That is going to be 500 pi. The integral of u to the minus 1/2 is u to the plus 1/2. And then we divide by 1/2 and plug in 5 and 10. And so this is 1,000 pi times square root 10 minus square root 5. Obviously, we can easily plot that into a calculation to get our estimate, because we were counting people here.